everyone, how are we doing? Who's all in the chat? It's time for questions. Drop your questions in. Let's get working away. What are people wondering about? Let me know. Hey, what's up, Blake? Good to see you here. Who is all here in the chat? I never looked to see, excuse me, how my fantasy team went last night. Fantasy team. Checking out those fantasy points. Holy mackerel. I got 125 and my cousin got 107. Who did amazing. And I got the team still playing tonight. They can't get tons of AJ Brown, Travis Etienne. AJ Brown just went, no way. How do I? Wow. And Jalen Waddle. My cousin's got to be like, no way, Brian. What? I might be the top scorer of the week. Yeah. I got the most points. What in the world? Well, amazing. Yeah, I'm in a, what is it? Whatever my league is, I have a little bit less. Aim for 13K points for Office Hours. Nice job, Lachey. Good to see you, Sarah, Jackson, Victoria. Drop whatever question you have in the chat. Yeah, my top players this week. Brown, Waddle, Etienne, really crazy points. My cousin had Tago Valera. So he got 107. He got the third best score in our league. One of my other cousins had Kamara, Foreman, and Smith. So a really good play right there. But my cousin's probably like, no, how did Brian do so well? He's probably bummed out right there. But really good, man. My team's been all right. I'll be 4-4, and it's like all tied up in my league. But what questions do people want to do? Drop those questions you want us to do in the chat. We're just chilling out right now until we get some questions. So what questions do you want to do? What questions? I'm 7th in the league overall. Oof. Yeah, it's my comeback week. I'm 4th in my division. Yeah, there's my aunt's number 1 in the division. This will help out. This will help out a good bit. Well, I'm not going to win to her in the division. I'm not going to win the division. Huh. Wow, the other division is 4-3 is the best. How is the... Let me look at the Charging Buffaloes. And then... Are they losing this week? Did my aunt... My aunt lost. Oh, both teams are losing that are ahead of me. Chapter 12 quiz. The probabilities that an adult male has high blood pressure and or cholesterol shown on the table. Let's do it, Wes. And good to see you here, Wes. I was looking at my fantasy team in the background. Got to find those probabilities. I love mathematics. I love probabilities. And that's why I love fantasy sports, is because it's based on probabilities, and, sports is fun to like do mathematics on. So nerds like me can be like, hey, we like it. We like doing it. So this is supposed probability. Oh, nice. We'll do the bus one. So let me get right here. The high blood pressure. Okay, we got that one. Let's get the bus one. Oh, from Canvas Content. Okay, we'll do the bus one from Canvas Content. Yup, that's a good one. So we'll do the first two here. Drop those questions in the chat. I'm trying to find Wes's question. Some of these are pretty easy, and then there's some tougher ones. A lot of them are repeats from the homework. So, laptop one. Gotta find it. We are near the end. Mars candy bars. Blood types. There's the light bulb one. Oh, it literally is the last question, Wes. I was worried it wasn't there. Okay, let's head over to the main screen. Here we are of the probabilities of high blood pressure. So let's take a timestamp right here, 523. Stat 201, chapter 12 quiz. Literally the last question. I was like, where is it? Okay, so here we go with the question. It says the probabilities that an adult male has high blood pressure and or cholesterol shown in the table below. Something tells me that they're going to be dependent. So what is the probability that a man has both conditions? Okay. So here is the probability of having both conditions. It's just asking you to read the table, I believe, because this is high blood pressure and high cholesterol. So the probability of both conditions is that. Does that make sense right there? Yes or no in the chat. It's just asking you to read from the table. You're saying somebody in this quadrant right here has both high blood pressure and high cholesterol. So the probability of having both, according to the table, is 15%. So that's just the probability right there. The probability that a man has high blood pressure is this. So now we're looking at just high blood pressure. Let me see, because now I'm getting a little. What's the probability that he has high blood pressure? Now I think they're not saying both right here because they're just saying has high blood pressure. So once again, they're asking us to read the table right here, and we're seeing the probability of high blood pressure is this right here, 0.16. So the probability of high blood pressure is 0.16. That is just blood pressure high right there. That one right there. They're saying 3 decimals, so I'm a little worried. The probability that a man with high blood pressure has high cholesterol. So now they're saying, given a man has high blood pressure, what is the probability he has high cholesterol? So what is the probability that a man with high blood pressure has high cholesterol? So the probability of a man, let me see here, with high blood pressure, oh, geez, because we're going to have to round it. With high blood pressure, so high blood pressure has high cholesterol. And this table right here shows everything. So this is the percentages of a population total. So we should be able to go right here. And this is 31% of individuals. And we're talking about that 15%. Let me double check. The probability that a man with high blood pressure has high cholesterol. I think B is... let me look at B again. The probability that a man has high blood pressure. Oh. Well, wait a minute. No, I think you're right. I think I did get B wrong. Because I think it's using the addition rule. The probability that a man has high blood pressure is not 43.4. What is the probability that a man has high blood pressure? Brain is still waking up. What is it? I'm displaying it on here in yellow, Wes. This is all the probabilities right here assigned. What is the probability that a man has high blood pressure? Hint, let me put a star and show it to you this way. What is the probability that a man has high blood pressure? What is the probability that a man has high blood pressure? The probability that a man has high blood pressure would be the percent of men who have high blood pressure, which would be 31%. Does that make sense? How's that looking right there, Wes? So the probability of having high blood pressure would be 31%. Because it's just all the people right there who have high blood pressure, the percentages. Yeah. So even I made an error. Good call on it. I don't know why I picked the other one. My brain was just not on. And so now we have the probability that a man with high blood pressure, which is 31% of men, has high cholesterol. And that's 15% of the 31%. So we would go right here. We'd go 15 divided by 31. And there's the answer right there for this one. There we go. Round. The probability that a man has high blood pressure if it is known that he has high cholesterol. So they're saying if someone has high cholesterol, what is the probability of them having high blood pressure? So this is kind of a reversal of the way the table's drawn right here. It's doing another conditional probability. And so we're saying if they have high cholesterol, what is the probability of high blood pressure then? And so that would be the total sum of individuals with high cholesterol. And now the probability right here. And there it is right there. So that is the probability of high blood pressure given someone has high cholesterol. So it kind of goes back to the conditional probabilities we did earlier on test 1. A lot of overlap between knowledge. And that should be right there, 3.66. We should get everything correct. Yay! Good stuff right there. A little tricky. Thank you, Wes, for catching on the error on the second one. Don't know why I said 16% or something. I don't know. Just reason you're wrong. W right there. We got those W's. That was a good tricky one. Little tricky question right there. We can do more on the my Pearson quiz, but good stuff right there. Make sure to be able to draw these out and think through them conceptually. This is where the learning occurs right here. Yeah, and you just want to make sure you can draw it out. Like, given someone has high cholesterol, what's the probability they have high blood pressure? So the percent of people with high cholesterol, is 41%. 15% of those individuals have it, or 50% of the total. 2015, yeah, let's do that one here. We'll do the Canvas content next, or right now, and then we'll come back here. Wes, we'll do that one next. Thank you, Wes, for these great questions, and we'll make sure we get them right. Okay, there we go. Let me drop this in as Chapter 12 quiz, and stat 201, Canvas content. Yeah, let's go here. Canvas content. All right, let's check out that Canvas content. I'm materializing on the screen. Okay, Canvas content time. Then we'll come back and do more quiz. And whatever class you're in, come in and say hey. Oh, it says changes not saved. Save mod changes. We're looking for the one about. The question was, suppose the probability of a bus. Suppose the probability of bust. That's a tough one. I'm gonna find it. Here. 2 moments. Gonna find it. Drop more questions in the chat if you got them. Wes has the next one after this. Oh my gosh. There's so many versions of this. It's really good then. Oh. Surely we'll get it on the next attempt of reloading the Canvas content here. No? Okay. Three more tries. I'm going to go to the question bank. Try to get it. Suppose the probability. Oh my gosh. It's a good question right there. It's very similar. This is the question. Question being asked about is a complement question. So the complement is going to be used here. I can mimic the question. I know it well enough. The bus question about missing the bus multiple times in a row, and so we can mimic it. But I want to find it. Mark it. Really? Where is it? It's Canvas content, right? How could I generate this many versions of it and not see it? Well, let me go grab it from the test question bank. Thank you, Sarah. Oh my gosh. See, these are independent trials of me generating this. Because each time I generate it... Oh, wait. I literally just found it. Let's go do it. Oh, wow. You got a tough one then that rarely appears, but it's a really good one, and it uses the complement. Okay. So we have here the Canvas content question about suppose a bus arrives on time. Or doesn't arrive on time. So let's think about how this one goes right here. And these are some of the toughest questions on the test. So suppose the probability of a bus arriving on time is 0.6. For the next 3 stops, what is the probability the bus is on time for at least 1 stop? Now, there's some important words you should see right here, like assume independence. If you assume that things are independent, what does that mean you can do with probabilities? Assuming independence is related to the what rule. What rule? Good job right there. Kyra, we'll do that one here coming up. What rule requires independence? What rule requires independence? So what rule requires independence? What rule? Remember from the notes, there's a rule that says 2 things must be independent to what them together. What rule? So I have this written down, have it on your note cards. Multiplication rule. Great job, Blake, right there. The multiplication rule requires independence. You want to make sure you have that on your note cards, where you have the multiplication rule requires independence, and we can multiply them together. So let's see what the question's asking. It wants us to talk about the probability that, what is the probability the bus is on time for at least one of the stops? Okay. So let's go over here to a Word document. On time at least once. Not sales promotion. So on time at least once. What does on time at least once look like? Well, if there's 3 stops, if it's on time at least once, then it could be on time every single time. How about this? The bus could be on time 2 out of 3 times. The bus could be on time only 1 time. But if it's on time at least once, it can't be what? This is where you have to think through the theory of it. If it's on time at least once, it can't be what? Green represents on time. So if it's on time at least one of the 3 times, it can't be what? If it's on time at least 1 time, it can't be what? And if you say it can't be late every time, right? Great job, Sarah, right there. So it can't be late every time. So you've kind of solved the answer right there. You've solved the theory behind it, because the bus will either be late every time or on time at least once. Does that make sense theoretically right here? The bus will either be late every time or on time at least once. So these two events are what of each other? So the bus will either be on time, it'll be on time at least once, or late every time. These two events are what of each other? We can add them. They're many things. They are what? Because the bus is either late every time or it's on time at least once. One of those things must occur, meaning these two events are what of each other, now that we've labeled them this way. They're very dependent. They're very dependent, because if the bus is late every time, then it can't be on time at least once. They're very dependent. But the fact that it's everything that can occur means they're what of each other. The fact that they are everything that can occur, so this is every single thing that could occur right here. I've listed everything that can occur right here. The bus is either late every time, or it's on time at least once. It's either late every time or not late every time. So I have given you what's right here, because I'll say it this way again. It's either late every time or not late every time. So it's either late every time or not late every time. So it's either late every time or not late every time. These are what's. So bus is either late every time or not late every time, which means it's on time at least once. They're what of it. So remember the rules, remember the words. The bus, that means they're what? They're also that. They are disjoint and they are complements. So complements are disjoint, and so they are complements. By saying the bus is either late or not late every time. So they are complements. And complements add up to what? Complements add up to what? Complements add up to what? If two things are complements and we add them together, they add to what? And we did that in class today too. If two things are complements, they must add up to what? If you have A, not A, because the bus is either late every time or not late every time, the two things that are complements must add up to 1. Great job, Blake. They add up to 1. So now that we know this, how could we solve for the probability of, we're trying to find on time at least once. How could we solve for the probability of that? How could we get the probability of on time at least once? And this is the stuff you have to practice. These are the tougher questions. Like, you want to map it out like this and try to draw it out and practice solving it. Like, try doing this one without me and see if you can solve it. Like, the more you practice it, the more you solve it, and you can just do it, the better you get at solving these and understanding, like, how to talk about probabilities. Like, it is either the case that the bus is late every time or it's on time at least once. Those things can't overlap, thus they're disjoint. It's everything that could occur, thus they're complements. Complements add up to 1 because it's either A or not A. So here we have, how are we going to solve for on time at least once? So what would be the mathematics to solve for that? So now we want to solve mathematically for on time at least once is equal to what? So do some algebra right there. Well, we will. And but how would we algebra this out to solve for that green one? So how can we algebra for that answer? So use a little bit of algebra right here. How can we algebra to get that answer? So try doing some algebra on that. So use that up there and do algebra. And how would we algebra the answer? Bring the other thing over to the other side. Does that make sense right there? We're just algebraing this over to the other side. We're just taking it and saying mathematically, if you just, it might be easier if I just call this x and I call this y, and x plus y equals 1. And thus, if we go right here, this is simply y equals 1 minus x. Does that make sense? So if x plus y equals 1, if x plus y equals 1, then 1 minus x equals y. Does that make sense to see it that way? Because x and y, when you add them together, equals 1. So you could just subtract x off of 1 and you'd get y. So it's like, if x is equal to 0.6, what is y equal to? If x is equal to 0.6, what is y equal to? If x is equal to 0.6, what is y equal to? So if x is equal to 0.6, what is y equal to? 0.4. So they're just complements. Does that make sense? So complements is you just find what adds up to 1. So you could subtract off, or you could also think what adds up to 1. So that's the same thing we're doing right here. This is the same exact things. It's the same math. So now what do we need to solve for? We need to solve for the probability of what? To find the answer for at least one time, we want to find this right here. We need to find the probability of what to solve for that answer. We can just call it x if you want. We're trying to solve for y. You can just call this y. So now we need to find the probability of what? And subtract 1 from, do 1 minus that. We need to find the probability of what? We need to find the probability it's late. We need to find the probability it's late every time, right? Being late every time, right? Well, so the probability of being late is what? What's the probability it's late? So be careful. What is the probability of it being late? So the probability the bus arrives on time is 0.6. What's the probability of the bus being late? 0.4. What is the probability of the bus being late and late and late? So what is the probability of the bus being late and late and late? Assuming independence, which the problem tells us to assume, what is the probability the bus is late and late and late? I think that's right. Yeah, it does sound right. So 0.4 to the third power, or 0.4 times 0.4 times 0.4, because what's probably it's late and then late again and then late again. And so what do we do once we find out the probability of late every time? Is it, we'll do y equals. Does that make sense right there? How are people doing? Does it make sense, Sarah? This is and then we just solve for what y is. So we want to find the probability of on time at least once. Well, that, oh God, great work, Sarah. This is a tough one. This one requires a complete understanding. And we're about to do the soda one coming up here. I might do the soda one next because the soda one is nearly identical to this. So we're going to do the soda one next. I'm going to do a jump in the order. It's this one right here. We should get a, whoops, wait, yeah, it is because I was subtracting. We should get a 2 out of 10 on this. So don't worry. I know sometimes I don't make a perfect grade, but 2 out of 10 because we only answered one question out of the 5. So that's why we didn't get the perfect grade. So I was like, oh my gosh. No, don't worry. We wanted that to be a 2 out of 10. Let me go bring up the soda question, which is nearly identical. Perfect. Okay. So let me mark this and we're going to move it around. Then we'll do Wes, your question here next. But this question is nearly identical. I want to show you how quickly we can solve these questions first off. So give me a second to mark this. And then I'm going to show you how quickly you can solve these questions if you know how to do these. You ready? If you buy a 6-pack of soda, what's the probability you win something? So, okay. 2, 3, 4, 5, 6. There. If you know how to solve them, you know what you're doing theoretically. Let's talk about how I solved that. So we have to think about what's going on right here. The question asks, for a sales promotion, there are winning symbols under 17% of the caps. Does that make sense? Just repeat to me, what percent of the time do you win? So what percent of the time do you win right here? Just repeat to follow along. What percent of the time do you win with this sales promotion? With this sales promotion, what percent of the time do you win? What percent of the time do you win with this sales promotion? Just to repeat to follow along, what percent of the time do you win? What is the probability of win? So we want to make sure we write this. Probability of win is equal to 17%. Great job, Sarah. Let me throw, I haven't thrown out points today. Maybe that's why we get everyone waking up right here, get some points. This is a good review of just what we did a second ago to see if we know how to solve it. So now you're going to buy a 6-pack of soda. Does that make sense? What would you like to do in this 6-pack of soda? What would you like to happen when you buy a 6-pack of soda? What would you like to happen? What would you like to happen? You'd like to win something, right? Tell me the way I'm drawing this right here. What does this mean for your sodas? Just the way I'm drawing it visually. My visualization right here probably represents somebody who bought a 6-pack of soda and what happened, just visually speaking. So visually speaking, I'm drawing the probability of what? You bought a 6-pack of soda and what happened? You won 2 out of 6 times. Now, if we know we'd like to win, what would we not like to happen? What would we not like to happen? Think about what you don't want to happen. You would not like to lose every time. Great job. And great job, Sarah and Blake, following along. These are the tougher questions. So we'd not like to lose every time. So couldn't we describe this in a way right here? Either when you play, when you do this, when you buy these sodas, you will either win something. Do you see it right there? Do you see the win something? The way I drew it, you will either win something. There's many ways to win something. Or no, not win something. I have just described the world with what's here. I said either you will win something or not win something. That is what will happen when you buy your sodas. These are what's of each other. These are what's of each other. They are complements, meaning they add up to 1. So we could just turn this into a plus sign right here and then talk about the probabilities. So now, what is going to be the easy thing to find? Because the way in which you can win something, which is what we're interested in the probability of winning something, could happen many, many, many ways. And shout outs to anyone who goes through and finds all the ways, the permutations by which these could occur. I would not do that. There's only one way you do not win something, right? So we probably, even though we're interested in finding the probability of win something, it probably would be easier to find the probability of not win something. So what's the probability of not winning? The probability of not winning, i.e. losing, or we could say, let's say losing, sure. Probability of losing is equal to 83%. 83% is the complement of that. So what is the probability of not winning something? The probability of not winning something is what mathematically? So this is the y, what we want to solve for. We're interested in the probability of win something. We'll solve for that here in a moment. We're just going to call it y because we're interested in it. Y, what's the probability of it? Blake, you got it. That's it. Because 0.83 is the probability of losing, and you lose 6 times in a row, i.e., you lose and you lose and you lose and you lose, and I'm multiplying these, and we are assuming that every soda can is independent of the previous soda can trial. Because when you open up a soda can, do you think it really matters to this soda can that you lost or won on your last soda can? No. The idea of independence is if you have an 83% chance of losing on this soda can, when you open it, you have an 83% chance of losing, independent of what happened on previous soda cans. So the probability of winning on each soda can is truly independent. Good question right here. So we just, all we need to do now is solve for y. That's it. You just go here and you say 1 minus or we could say y equals still. Y equals, we'll put the equal sign here. Bring this over to the other side. 1 minus 0.86 to the 6th power. And if you will, or third, 6th power, excuse me. 6th power right there. Oh my gosh, that's where I'm reversing things. But does that make sense, Blake, right there? So really good question again. Uses the same mathematics, hence why I did this one back to back. Great job, Sarah, right there. And that's it. And if you notice how quickly you can do these, if you know how to solve them, and you practice understanding how the complement works, this is the addition rule also. This is the multiplication rule. It uses independents to multiply them. It uses disjoint events, which are complements right here, to do the addition rule, because complements can be added because they're disjoint. Yeah, exactly. And I think drawing it out can help to be like, okay, I'm going to buy these soda cans right here. I've been working these problems for a decade, so I'm like, I have drawings. Like, this is one of my favorite ones because I know the drawing I do on it, and like, let's draw it out right here and see what would happen. I think it works better to visualize things. But this is a really good question, and we have questions like this on the test, like what's the probability of at least one? So you want to write it out like this, where you have you either win something or you don't win something. So the probability of winning something is 1 minus not winning something. So you just write the probabilities, solve it out, and have the probabilities associated with. Let me color code it a little bit more. If anyone's wondering, the color coding stays throughout. The y is what we're interested in. We're thinking about the probability of winning something. And the complement is the sum of the two events being the disjoint set of all events. With that, really good stuff. Let's do another one. I'll head back to Spike. I think it starts to fade again over when I go here. Okay. We only have one more question, so drop more questions if you got them. We have the 2015 study. The 2015 study. Max bonus. Keep it up, Blake. Excellent work. Keep getting those great grades throughout the semester, because it's always nice at the end to have that buffer on your grade to be like, okay, go into the final and be like, I just got to make like a 75. I love that. I've had people be like, I only have to make a 50 on the final to make an A. What do I have to do? And I'm like, just make a 50. And they're like, but what if I don't? And I'm like, if you made A's on the other test, you're probably, it's good reason to believe they're not independent. They are to a certain degree, but usually performance in a class is predictive of future performance. So keep working hard, keep practicing. These are our more mathy chapter. This chapter is very, very mathy. So I love it. Stat 201. Chapter 12, Quills. Here we go. Let's do it. A 2015 study found that 71% of adults aged 25 to 29 had a cell phone and no landline. Okay. That raised concerns about the accuracy of certain surveys. Sure. As they depend on random digit dials. Love it until you fail and then you hit it. Exactly. Researchers randomly selected. Complete the parts below. What is the probability that all of these adults have only a cell phone and no landline? Oh, they're selecting 4 adults. Okay. So the probability of having a cell phone and no landline is 71%. They should literally just, okay, that's all we need to know. So probability of cell phone, no landline is 71%. They talked to 4 people. What is the probability the first person meets this criteria, and the second person meets this criteria, and the third person meets this criteria, and the fourth person? So it's the keyword. Blake caught it right there. Blake, great job. And just the way, if you can talk about it that way, which I'm saying multiplying by saying and we're assuming independence to say that each person they speak to, it's not like a family, because then families would be dependent on each other. Like if you have a landline, your family members probably have a landline because they probably live with you, hence like close family. So we're assuming these are independent. So 0.71 times 2, 3, 4, and there we go right there. Round to 5 decimals. Oh my gosh. They want to make sure you did it. No way to guess that one. Is it going to be mad if we were to like not do it? What is the probability none of these adults, okay. What is the probability that none of these adults have only, so they're saying like, it's weird the way they're phrasing it. They're saying that they don't meet these criterias. So they're saying, what's probably that none of them meet it? So this is very similar. My Pearson does, maybe that's what happened. Too many people didn't round and my Pearson just stopped sending grades over. They're like, if you want to regrade everything, you can grade everything yourself, Brian. They contacted me back and they're like, have you tried this? And I'm just like, I just need someone to like jump on. It's the first time I've ever had a major problem with my Pearson. Usually my Pearson's very good. Usually. So what is the probability all four do not meet the criteria? So very similar work right here, Blake, to find this one. So it's basically saying 71% of people have X. What's the probability all four people have X? What's the probability all four people don't have X? So first person doesn't meet it, and second person doesn't meet it, and third person doesn't meet it, and fourth person doesn't meet it. So what's the probability of that? Yeah, I think you have it. I think I see what you're doing. 0.29 times 2, 3, 4. So it'd be to the fourth power. Does that make sense, Blake? So round to 5 digits again. That's ridiculous. So it'd be 0.29 to the fourth power because the first person doesn't meet it and the second person doesn't meet it. If you raise something to 0, it becomes 1. So it mathematically speaking, it's remember when you multiply, you're doing yeah, exactly. Because yeah, there'd be probability of 1. So it's just 0.29 times 0.29 times 0.29 times 0.29, abbreviated 0.29 to the fourth power. What is the probability that at least 1? So truth for this one, when they say at least 1, it's just going to be 1 minus one of those probabilities. So we have to think about which one it is. So let's see what they're asking. What is the probability that at least one of these adults has a cell phone and no landline? So they're saying this is everything but no one having it. So this is the one we want because this is no one has it and this is at least one person has it. Does that make sense? Because if this is the probability no one has it, either no one has it or at least one person has it. And we did the right rounding. I got scared with that rounding right there. So a little tricky one. At the end, make sure you realize that it's saying this is the probability no one has it, which is 0.29. They should just say cell phone. They should just say 71% of people have a cell phone. They should just leave it at that. And they say, what's the probability all four people have a cell phone? So if it helps make sense to you, you can just read it as cell phone. They should just say 71% of adults have a cell phone. And then they should say, what's the probability 4 random adults have a cell phone? 71 times 71 times 71 times 71. What's the probability 4 random adults, all of them don't have a cell phone? 0.29 times 0.29 times 0.29 times 0.29. What is the probability at least one has a cell phone? Everything but 1 minus all not having cell phones. Does that make sense? Good, tricky question. The wording just makes it more difficult because they should just say 71% have cell phones. That's got it. Well, what else? What other ones have we not done? Drop those questions in the chat. We've done like 4 questions today. We got to do some more. There's some really easy ones. What other questions do people have? I swear. I got like 8 hours of sleep and I'm still tired. The Mars Candy Company. Kira, you got it. Good to see you here. Let's drop some points. Thank you for being here. You can drop the questions at any time if you want. The Mars Candy Company. I saw that one. I haven't done this one yet, so let's see if I can get it right. It's a new one. The Mars Candy Company right here. More sleep equals more tired. Don't sleep. Facts. Okay, the Mars Candy Company. Let's make Kira a mod right here. Okay. The Mars Candy Company. I swear I did more than 4 questions today. Maybe not. Stat 201. 39, 23. Stat 201, Chapter 12. Quiz. Here we go, the Mars Candy Company. Let's knock the question off the board. Okay. So here we are at the Mars Candy Bar Company. And we got some probabilities right here. Yellow candies are 20%. Red are 20%. Orange and blue and green make up 10% each. The rest are brown. So if we draw this as a probability distribution, what percent of M&Ms are brown? Is that real? What percent of M&Ms are brown? So when you think about this, let's go right here. Let's write it down. You also want to write down what you're doing with these. So yellow equals 0.20. Red are 20%. Orange, green, and blue, 10%. Really? Orange, green, And what percent make up brown? Best I could do. It looks to be what? What percent make up brown? So to be a proper probability distribution, you must add up to what? So there's a rule of probability distributions. The sum of all probabilities must add up to what? So to be a proper probability distribution, you must add up to what? So this is the addition rule because an M&M can't be yellow and red as far as I've seen. They are one color only. So they have to add up to 1. Great job right there, Rhea. And so that means the probability of brown is what? So if they must add up to 1, try to do a little algebra right here and be like, how could I solve for this? We've done questions like this on the test. We've had like solve for the missing probability and the proper probability distribution. Brown equals, great job, Kira, right there. It's like a light, that looks very good. Looks like a nice milk chocolate right there. Kira right there, more points in the chat. Let's raise some more points. Keep up those questions / answers. So they might be asking this. I don't know. We always like to kind of write down what we're working with so we can see what we got. What is the probability that an M&M is blue? Well, it's just that, right? Let's see right here. Probability of blue is that. What is the probability of brown or yellow? So what can we do to these probabilities right here? Brown or yellow would be what? Great job right there, Rhea. Brown or yellow would be what? What is the probability of brown or yellow? Brown or yellow is what? Because if it can't be brown and yellow, so brown or yellow would be what probability? Brown or yellow would be what? Think about if I say, what's the probability it's brown or yellow? So you're saying this or this. What is the probability of that or that? Brown or yellow is what? And what would you do to those probabilities? Like you draw a random M&M out of your bag. What's probably it's brown or yellow? What would you do with those probabilities? And think of the word or. Because I have listed right now the probability. It's yellow, red, or orange, or green, or blue, or brown. So what would be the probability of yellow or brown? Add them. Great job. So 50%. And that's because they're disjoint. You can add them because they're disjoint because an M&M can't be... If an M&M is brown, it can't also be yellow at the same time. So disjoint probabilities can be added. That means that if it is brown, it can't also be yellow. Remember, disjoint means if one thing happens, the other thing can't. You get a brown M&M, you didn't get a yellow M&M. The probability that the M&M is not orange, well, that's just what? How, when we say not, what rule are we talking about right here? And how can we find the probability of not orange? What is the probability of not orange? So this is using the complement rule. And what is the probability of not orange? This is a very good question on like basic, a lot of the rules of probability right here. So what is the probability of not orange? How would we do that? It's the complement rule. And how would we get not orange? Exactly, Kira. Great work, Kira. Yeah. And is it Kira or Kyra? Make sure I get it right. Oh, whoa, look at that. I'm going to make errors. Tons of errors. The probability that the M&M is striped. There's no striped M&Ms, right? I assume there's no striped M&Ms. Like they're pulling a weird one right here, right? Oh, just felt a tinge in my shoulder as I leaned down. Okay. Assuming an infinite amount. So they're saying they're trying to do okay. What is the probability that they're all blue? We're going to draw 3 M&Ms in a row. Okay. So you're reaching into this infinite bag of M&Ms. You've asked the universe to give you infinite M&Ms and need that infinite supply of M&Ms, right? So when you pull out your first M&M, it was what? You pull out your first M&M and it was what? Just imagine we're doing this question right here. You pulled out your first M&M and it was what? You pulled out your first M&M and it was what? I think it says that right here. It says it's saying that it's saying that it should be more specific. Rhea, I think it's saying, unless I've made a misinterpretation of this question, it's saying that orange, blue, and green each make up 10% respectively. Because they're trying to be realistic towards the M&Ms. Because if you buy M&Ms, there's some orange, there's some blue, some green. they're like the lesser of the colors. If they're being true to it right here, it wouldn't be that they are only 10%, because then that would make up 50% brown. And I think they're pretty accurate in how M&Ms look distribution wise. Lest Mars get mad at them being like, no, our M&Ms have a totally different distribution. But I don't know if they're going off their website or what. But so they are 10%, like blue makes up 10%, green makes up 10%, orange makes up 10%. The orange, the blue, and the green each are 10%, 10%, 10% respectively. Like for each one. Yeah, no, good question. And if they're going a totally different way, it totally changes the question. So that's one of the points I like to do here too. I'm 99% certain we're right on this. I could be wrong. There's a new one this semester. But as Blake's pointing out here, with 3 M&Ms in a row, you're welcome, Rhea. Thank you 1,000 points for asking. I always ask these questions. With us pulling 3 M&Ms, the first is blue, and the second is blue, and the third is blue. So how would we solve the probability of getting a blue and a blue and a blue? So we're going to pull an M&M. It's blue, and then the next one's blue, and then the next one's blue. This is the what rule, and how do we solve for it? So each one has a 10% chance of being blue. So the first one was blue, and the second was blue, and the third one was blue. So what is the probability of blue and blue and blue? And I'm saying it mathematically right there for you. So what is the probability right there of blue, and then blue, and then blue? So the probability of a blue M&M is 10%. So what is the probability you get a blue one, and then you get a blue one again, and then you get a blue one again? The word "and" denotes we're using the multiplication rule right there. So we multiply the probability of a blue M&M times the probability of a blue M&M times the probability of a blue M&M. And so that would be the probability right there of getting 3 blue M&Ms in a row, which should be equal to 0.0001. I said one too many zeros, I think, when I said it. 1, 2, 3. There it is right there. The probability of the third one being the first green one. I have done this one before. It's reminding me of it. Okay, so this one's tricky. If your third M&M is your first green, then your first and second M&M were what? If your third M&M is your first green M&M, then your first and second M&M were what? If your third M&M is your first green, well, they could be blue, but if they were not green, right? So the mathematics for this is going to be the probability of not green times not green times green. So what is this mathematically? Just think about green is this, not green is this, and I think I know the answer. You just move the decimal on it. So it should be 0.0. Yeah, 0.081, right? 0.081, I think, because 9 times 9 is 81, times 0.1, move the decimal, 0.081. So 0.9, because that's the probability of not green. So Rhea right there has the probability of not green times the probability of not green times the probability of green right there. And because it's either green or not green. So this is the third M&M is your first green. So your first was not green, your second was not green, and your third is green. Probability of not green, green is 0.9 times 0.9. So sub in the probabilities and kind of think what happens when you pull your M&Ms. Not green, and third one green. Lot of good stuff right here. So that is a good one. So far, I love this question. Don't ban this question. Don't ban it till I miss a part, and then we'll say ban this question. What is the probability that none are brown? None are brown. So you're going to pull 3 M&Ms, right? The first was not brown. The second was not brown. The third was not brown. So we need to figure out over here the probability of a not brown M&M. What is the probability of a not brown M&M? Yep, Blake, that's exactly it. Blake, you got a lot. This is great stuff, Blake. Blake is solving it out mathematically. And Blake, you've done it. So about half. It's going to be about 0.3. Wait. Oh, man, I can almost do it. Oh, it's 0.34 something. 0.347, I think. 0.347. Let's see how close I was. No, 0.248. 0.248. Wait. Okay, I was better than my other guess. Just don't listen to me. Doing it wrong in my head. I should have 0.347 was a good guess. The other one was a horrible guess. My brain's like not working. Okay. So it wants that right there. The probability of at least one orange M&M. So this is the complement rule here again, where it's either the case that none of our M&Ms are orange or there's at least one orange. So this one right here would be either none of our M&Ms are orange or at least one is orange. So let's write that out right here. It is either the case that we get no orange, so no orange, or at least one orange. And that's what we want to find. And that equals to 1. So what can we find right here? It is either the case that we have no orange M&Ms or we have at least close. So when we do the probability of no orange, we're not talking about just one M&M being drawn. You're basically right. You want to do all 3 M&Ms are not orange. Does that make sense? Your first M&M was not orange, your second M&M was not orange, and your third M&M was not orange. So now when we algebra this over to the other side, it's going to just go over here to 1 minus. Oh, wait, I can't do it right there. Yeah, so this is all 3 M&Ms, not just one of them. It'll be 1 minus 0.93 to the. Oh my lord. There we go. And this is at least 1. We'll call it that, at least 1. And this is this, at least 1. Just abbreviating right there, and there's the algebra. And this is what we wanted to find the whole time right here. We wanted to find the probability of at least one is orange. So it's going to be like 0.72 or 73. So about 27%. So let's see right here, about 27%, I say. Yep. There it is, 27.1. That should be right. Longer question. Let's hope we didn't make an algebra error. Still waiting for that infinite benefit M&Ms. I am too. 100%. I was worried. I was never worried. I lied right there. I'm not worried. That was a really good tough question. Lots of math right there. Lots of multiple solves. The striped thing was just weird. A striped M&M, there aren't any, so the probability is 0. They should say like M&M doesn't make striped M&Ms. That'd be nice if they clarified that. Probably we got that right as 100. Oh, Rhea right there. I like that. Rhea, let's throw that as a quote of the day and give you 1,000 points right there. Throwing that positivity. Everyone's I get anxious if we miss something, and it makes me more anxious. So I'm more likely to miss a question. You talk about dependent, independent, quote 329 right there. Brian is more likely to miss a question if we just missed a question. So when we go on streaks of getting questions right, I get this like boost and I'm like, we'll never get anything wrong. And then as soon as I miss something, I'm like, oh no. And then I start forgetting to check things, like double checking my work, making sure decimals are right. Like just, like little decimal error here, decimal there, error. Because we'll go like a week without missing anything. Then we'll have like a day where we miss like 5 questions. We'll be like, oh my gosh, can't get anything right today. I feel like the only ones we miss are the ones where my person doesn't like. Yeah, that's a very common thing too. So we're always trying to watch that rounding on it and make sure we read like each time. But once again, always let me know on the rounding. And if you have another teacher too, if you're watching this for another class, they should be nice on it. It's because Mercury is in retrograde on those days. Maybe it is. You never know. What the heck is Mercury doing? This one right here. Watch this. You ready? So this is the light bulb one. Are you ready to see if you can solve this? 90% of variation can be explained. That's the R squared, is it? Blake doing some R squared on it right there. I like that, Blake. So that was a longer question. That was a really good one. Okay, so let's do this one. Watch this. This is another at least one problem. You purchased. Okay, so a 5-pack. So you ready for this? How quickly? I'm not going to read it. How quickly do you think I can solve this question? What do you think? 2 minutes, 3 minutes, 4 minutes? We want to know how to solve these. How quickly? I'm not looking at it. Once I see the numbers, I'll know how to solve it. 2 minutes. 2.1 seconds. I like the variation. I'll tell you this much. It'll be between that. Let's bring up the speedrun clock right here. Have a little bit of fun. All right, so let's get the speedrun clock going. Stat 1 speedrun is going to be right here. I'm trying not to look at the question as I bring up the speedrun clock. All right, so we got the speed run clock over here, and we're starting the clock. Okay. 5 pack of light bulbs, 24% recall. What's the probability at least one of your light bulbs is defective? So 1 minus the probability of all of them working. So probability of, really? That's just eating up time, right? Oh my, I lost 5 seconds of that. Probability of a working light bulb is 0.76. First works, second, third, fourth, fifth light bulb. 1 minus all working is at least 1 defective. 3 decimal places. That should be it right there, and clock done. I lost like 5 or 10 seconds. Because it's either the case that all your light bulbs work, or at least 1 is defective. So did everyone hear that? It is either the case when you buy your light bulbs, you're buying this pack of light bulbs. It is either the case that what about those light bulbs? You just bought a 5-pack of light bulbs. It is either the case that this 5-pack of light bulbs, it is either the case that what? It is either the case that what? What would you like for this 5-pack of light bulbs? So here we'll show it here. We'll do the steps again. And just very important to know how to solve these and to be able to understand the mathematics behind them. It is either, great job, Ria, right there. Great job. It is either the case that all the light bulbs work. So you're either going to be in one of 2 worlds. And when we do these 2 worlds right here, in a world where your light bulbs work. So you are either in world A, buy the 5-pack. Here's world A. All your light bulbs work. Or you are in world B. Now, this is just one scenario in world B. In world B, what? Which is what we're interested in. In world B, what? In world B, notation. Not all the light bulbs work. That's a, wow, Ria, right? Great job way of saying it right there. Not all the light bulbs work, which means at least 1 doesn't work, right? So it's either the case that all light bulbs work. Ria, that was excellent right there. That's exactly the way to express compliments. It is either the case that all light bulbs work, or, and there's the or, not all work, which means at least 1 doesn't work. So we could say all work, or, and this is just another way of saying it right here, either all work or at least 1. And these both equal to 1. So just knowing how to talk through this. Does that make sense? Yeah, so let's still get 5,000 points. Keep it up. We are just here for that positivity. And Ria and Blake, and where's Evan at? Be working these problems, know how to solve them. The more you practice these, the more they make sense. So clearly, the easy thing to solve for is what? We have the probability of not work up here. So the probability of not work is equal to 24%. The probability of work is equal to 76%. Those are complements. So I'm on 12 stars. Oh, right. Are you in another online office hours? That's cool, Ria. Blake, good to see you. So what is going to be the easy thing to solve for right here? Who else? Someone else? Or do they don't do them on YouTube, do they? Ultimate Blake? Oh my gosh. Woo! Nice job. Ultimate Blake achieved. Blake, you got to show that off, Blake, during the next class. It's on Zoom? Cool. Cool. What's going to be the easy thing to solve for over here mathematically? What's going to be the easy thing to solve for? Ria's up there at the True Stat Nation level. We need to add in some more levels. So what's going to be the easy thing to solve for? The easy thing to solve for is going to be all work. Because the first works... Oh, wait. I got 6 light bulbs. So the first works, and the second works, and the third... I think it was your points right there, Ria, that got... Yeah, that was it. You got Blake to Ultimate Blake level right there. Blake has achieved his own level. This is what we're interested in. And that's it. So y equals 1 minus all work being this, which is the carryover from that. And there's the answer. I know, right? So it's, I love it that people, we're on test 2, and I love that people are getting to the 500,000. it's kind of I want people, if you've been going to class every day, I want you to get to the 500,000 kind of at the test 2 mark. Like that's when you've achieved max extra credit, because it's to get people hooked to the system. And we're doing pretty good this semester. We're hovering around 200 people watching live. So this is the answer right here to the question we just solved. We just solved this, and this is the work for it to practice and understand the theory behind it. How did you do that calculator quickly on the calculator? Just because I know how to think through it. I know how to, like, because I've done these so many times. I see it in my head. I think, okay, we want to know what's the probability that there's at least one defective. Well, either all the light bulbs work or at least one is defective. So 1 minus all work is the answer. All work is 0.76 to the 5th power. So 0.76 times 0.76. If you enter on the calculator on the screen, if you enter 0.76 and do times, whoops, I didn't hit times. If you enter 0.76 and hit times, you can do 0.76 and hit times. What in the world? 0.76 and hit times. You can go 2, 3, 4, 5. You can just hit enter. It will times it by itself. So you could also go over here to Google or anywhere else and do 1 minus 0.76 to the 5th power, and you could get the answer that way. So you could Google it too. That's a great way, but know how to solve it on at least one calculator. But on the calculator on a PC, I think it works on a Mac too. You do 0.76 and you do times, and then you say 2, 3, 4, 5, and then double check your work. Usually you might have hit it one extra time, and then we wanted to do 1 minus, and I did control paste right there, or copy paste, control C, control V. So just solving that right there and practicing. We did shout outs to, I think it was Shelby in class today. We did some really cool examples with questions like, what about if someone missed the first free throw? Could it like go up the other way? Because we saw ones that went down. Really cool things here with law of large numbers talking about free throws, where we actually saw someone miss a lot of free throws. And I got to do coding. I said if I did in 2 minutes, we could do it. So shout outs to my 320 and 474 students. We actually wrote a for loop right here that went through and found the probabilities at each point. So it's really just thanks to lots of probability practice. Do you have to hit equal 4 or 5 times like the 5? You hit it 4 times, because when you hit enter the first time, you're doing it for 2. So because you type it in, and that's like one occurrence, and then we do times, and then you're timesing it by itself. So you could do times and type it again. But doing it via this methodology ensures you don't type, because it's 0.76 we're going with, right? 0.76? Yeah, it is. So when I do this right here, I don't have to retype it. So that's the first occurrence. Hitting enter is the second, third, fourth, fifth, and there it is right there. So the first occurrence is when you type it times, and then when you hit enter, you're multiplying it by itself. And then it'll keep doing the 0.76 times whatever that value is. And we should be able to see it right there if you notice. It's just the way the calculator works. I've been using this for a long time. See, it keeps 0.76. If I hit enter again, it keeps the 0.76. So you're just constantly multiplying and doing powers of it right there. So you'll constantly do the next power. You can probably do powers of it too. If you go to the scientific version of this, you can probably just go scientific. So if you're over here, expand it. Or not expand it. So, there's x to the y. So if you go to the scientific version on the computer calculator, sure. Now you go 0.76 raised to the 5th power. There you go. Another way of doing it, just make sure it's done correctly, and probably try practicing on your calculator you might use for the test. So there's the same answer, and same answer right there. Then you do 1 minus, when do you do that way right here? 1 minus 0.76 raised to, oh, look, it's right in the full thing. Oh, you can just write it out in that. So pretty good stuff right there. Just make sure, double check your work. Make sure you put parentheses or whatever when you need it. But yeah, I never understand these M+. Memory add, memory subtract. That makes sense. Memory store. Yeah, I never used those. And there's like C and CEE or all those things. I never understood those. Can you do the after rolling doubles on a pair of dice 3 times? Yeah, let's do it. You bet. Thank you, Ria, for asking. A little more time. After rolling doubles on a pair of dice. A little chill music. We're over here. After rolling doubles on a paradise. Yeah. It's been a good day. I'm gonna play some video games later tonight. Relax. Let's go over to the main screen. After rolling doubles on a paradise. Here we go. And this chapter right here is one where you have to practice it. Okay, after rolling doubles on a paradise, sounds to me like we're talking law of averages, or which is a fallacy. After rolling doubles on a paradise 3 times in a row, your friend exclaims, "I can't get doubles 4 times in a row." That's a law of averages fallacy, because they're independent. That's literally they're independent. There is no law of averages, so I'm a little wondering about that answer. 3 rolls is not no. With so many doubles in a row, no. For the outcome of the dice roll to be truly random, the friend should not be making any predictions. Holding expectations for the results eliminates blindness. Kind of. A seems like viable. There is no law of averages for the short run. The 3 dice rolls do not. That's literally saying they're independent. Yeah. This one was kind of. And then 3 dice rolls do not. It could have just said this. Law of averages is there is no law of averages. It should say law of averages is a fallacy. Yeah. So preferably I would say law of averages is a fallacy. Law of averages is I'm due for this or this can't occur. Yeah. The right answer, once I read that, the 3 dice rolls do not affect the 4th. They're literally saying your 4th dice roll is what of the previous dice rolls. So this terminology right here, because if you're rolling dice, each dice roll some dice like that. Just, wow, dice. I wish I had some dice. Got a coffee cup. Rolled a coffee cup. They're independent. Exactly. So that's what they're getting at right there. Each dice roll is independent. The 3 dice rolls do not affect the 4th dice rolls. And there is no law of averages. There's just no law of averages anyways. It doesn't exist. It's a fallacy. There is no such thing as law of averages. There's law of large numbers. As we said today during class, law of averages is a fallacy. It is fallacious thinking. It should just say, I wish it said that. Like, that would be my top answer, would be law of averages is a fallacy. It doesn't exist. No one is due for anything, or less likely if things are independent. And yeah, any other questions? Let me know. We did a lot today. Probably did a good bit of these. So what else are people thinking in here? We could chill out for a moment longer. What other questions are there? You tell me. Whatever you're thinking. Let's see. So we've done most of these. We did, if you're wondering, from today, here's the things we've done. We've done the car questions. So we did a bowler, car questions, all these questions right here. We did the homework during class. Might head off here. Any other last questions? What are people wondering about? Just drop those questions in. Appeal. The answer is go buy one, Blake. How much does that cost? Let's go look at that. Let's go find out the cost. Cost of Peel P50. Yeah, it's only $13,000. We could do the Peel Trident. You can build this adorable. Is it a kit? You can make it out of a kit. So there, we're gonna Peel P50 or the. This is Blake and I's dream car right there. It's our the dream car. The world's smallest car is back. An original Peel would have a cost of $2,200 in today's money. It's literally just like a box with an engine. That's the cutest car. With an I, not an L. Alright, let's see here. Alright, here we go. Well, this thing's not as... These are 31,000 they're saying? I mean, it's still really expensive. It was like old school. Let's see, how does it look? Oh, wow. Look at that. Looks like he's photoshopped in there. That is just like... It totally looks photoshopped. Look at that guy right there. That's like me. That dude is going to get in there. Oh my gosh. The BMW... I said it. It's a BMW? Apollo IE, though. Now I want one. Was that Doug from a YouTube channel, is he? Is that... Yeah, it's got 6.6 million views, so you might know who that guy is, it sounds like. Yeah, so that guy right there. I have no idea. I'm not a car guy, so I don't know who these people are. Oh my gosh, yeah, this car. Oh my gosh. How much did you say this one? The multi-million Apollo IE Red Dragon. What in the world? The car looks like it could looks like the flash is about to like break the 2.6 million. I mean, it's only as much as like I saw a house in Knoxville was 2.5 million, around 2 through 3 million. So Blake, if I gave you the offer of, and let's say every tax is gonna like whatever I give you, you will not incur any more costs on. Does that make sense? So whichever one I give you, most expensive car. What was the 36 million? So Blake, you have this option. You ready? Whichever one I give you, you will not incur any costs on. There will be no property tax. There'll be no HOA. There'll be no gas for this. There'll be no repair fees. There'll be no fees. You ready? You have the option, Blake, right now of a $2.5 million house. Remember, there are no fees. The gas, the water, everything, anything this house incurs, you're not going to get any more fees. The car, the upkeep, the anything, someone hits your car, we're going to repair it fully. Every upkeep, you can take the $2.5 million car or the $2.5 million house. Which one do you take? Like, everything's paid for with all of them. Like, you take the house, heating, water, electricity, everything's paid for. Groundwork, everything paid for related to the house, everything paid for. You'll never incur a cost on that house. Car, everything's paid for. All the gas, anything, someone rips the leather in your car, paid for. Someone spills coffee, we totally redo the interior. Everything's paid for with both of these. You take the car, $2.5 million car, or the $2.5 million house. Which one do you take, Blake? Which one do you take? Very interested to see. Yeah. I thought you might go car though. I thought I could convince you. Yeah, with the house, right? That's the rational choice, but it'd be cool to have the car, right? There's a really cool $2.5 million house in Knoxville. Can I show houses here on Zillow? There's a really cool 2.5. My wife and I are looking at houses in Knoxville. There's a really cool 2.5. We're just having some fun at the end of office hours. Ferrari GTO. Okay, so now Blake. Okay, ready for this, Blake? Is this the crazy expensive car before we go to Zillow? Wait, is this one 2. How much does this thing cost? Yeah, but here's the thing. Okay, so I'm going to give you one of these two cars, Blake, but you can't sell it. You're going to make no money from this car. So you can either have, you're going to make no money. You got that? You can either have, and both cars will be street legal. So both cars will be street legal. You can either have this car right here. You can't sell either of them. So you can't be like, well, I'm going to buy it and sell it. You're either going to have the Apollo Intensa, and we'll let you have whatever version you want, or you can have the Ferrari. You're going the IE? Yeah, I know. That car just looks so insane. Yeah, I know. It's like, you're right. Like, this one's just expensive because it's like it doesn't exist other than probably, yeah, I mean, that car looks like you're Bruce Wayne, ready to that. Yeah, I totally agree with you, Blake. We're just having some fun for our last little time in office hours. I would totally go this car too. Like, because you could break the thing by being like, well, I would just sell the super expensive car. I know it looks super cool, right? Pagani Hyera Roadster BC. Is that your dream car, Blake? Thank you, Blake, for all the fun right here. And Ria, so glad we're just chilling out and having a little fun here. Let's turn a little chill music. We're chill. Oh man. Here's someone who actually owns one, it looks like. Ah, this car looks cool. Pronounced Wyra. Wyra. Yeah, this car looks really amazing. Yeah, that. Wait, is that real? Looks insane. Yeah, I think I might like this one better. Yeah, I feel like it would too. Maybe not this one right here, probably. Like that one, this one looks a little like YouTuber who just got a bunch of money. Maybe Tony Stark owns that one. The guy started the company after Lambo didn't listen to him. Nice, and he made these cars. These like really insane. There's one in a showroom. It looks like. Is that real? Man. So why don't I just make? Man, that looks cool. Yeah, look, this is someone's garage right here with like, you know, all the glass. It is like Tony Stark's garage. All are real, yes. That's the dude's name, is it? King's. Jeez. Yeah, these are insane. That's really cool. I mean, I'm not a car person. I'm a tech person, but you know, you can show me some cool cars. Maybe the Ajera RS. Cool. Thank you, Blake, for all the cool suggestions on cars. Oh yeah, this car looks. Is this obtainable? Oh yeah, I looked up the exploded view on Pagan. Is this an obtainable car? How much is this car worth? Ajera RS refinement is so. This is more on the dude's cars. Yeah, it looks really cool. Man, it's the low ceiling. I don't know if I'd like that. Several million. Well, I'm never buying one of those. Top Gear. Yeah, Top Gear magazine. Yeah. What kind of engine? 5.0 liter twin turbo V8. That's insane. Bye, Blake. Awesome. Just having some fun here at the end. Insane. Really cool. Man, I think that's a 2015 car right there. Why don't they make more cars that look like this? So, Blake, why do they not... Okay, we're just going to zoom in like crazy. Why don't they make more cars that have this really amazing look to them? I mean, how hard is it to make metal in these shapes? No, that's fine. I might talk about houses or something. How hard... Like, why is it so hard for someone like Honda to be like, oh, it's carbon fiber? Is carbon fiber like super expensive? So, but is carbon fiber going to be like extremely light, extremely durable? Okay, so yeah, because this one they like Kevlar out of, didn't Kevlar carbon fiber? They put like, I'm trying to think what they put in that. I don't know. It's interesting because you want, I mean, so these cars are actually like good quality, not like some sort of like, I don't even know, cost. Like, what costs so much? Why does a $5 million car cost $5 million? Does that make sense? Is it scarcity? Like it's a small amount of build? Because they just make the coolest looking cars and they make them cost $5 million. So why not start a car company, make your cars look super cool? I mean, it's like, is the engine like really that super expensive? You can't get that engine. Is it like a specially built engine that you're not going to find elsewhere? Engine materials and stuff. Like, what is the, like, if you could itemize the cost for me, I wonder if someone could itemize it and be like, okay, so the carbon fiber brings up this amount, the engine brings up this amount, the, you know, design aspect of brings up, because a lot of it I think is most cars of this nature have extremely rare and expensive material. Okay, yeah, just like some like gold pedals or something like that. Of course, gold is like more malleable. I mean, even because the wheels look cool. Yeah, I don't know. I'm one of those people that like when I buy my next car, it's going to be totally like, I don't know. I might buy a nicer car, but it's going to be very economical. Like, but I heard the issue with Hondas and Kias that there was a problem with people breaking into them. So I'm like, well, dang, I used to buy Hondas and they didn't address that. So that makes me have a lot of doubt in the Honda company. I have a Nissan Altima right now. You'll never look at doors the same. Look up the doors of the opening of the doors. So yeah, let's hear. So Blake, you need to help me out. Brian's next car should be a what? Brian, are they gull-wing doors? You know, I'll have some gull-wing doors. Oh, whoa. Here, we'll tell you. Oh. If I hear in the audio right there, it's some dude's random thing. Dehydral. Oh, okay. So I'm gonna play. What in the world? That is nuts. Here, we'll play that tiny bit. Yeah. Oh, sorry. I already played it. And I was like, what? When you hear me saying what in the world, when I was like, that's insane. I was like, what in the world? I was like, he's just lifting it up. That's pretty crazy. What? That's cool. How it connects in. That's cool. Live reaction. If you don't copyright claim me on my channel on this channel, please don't. I don't want these office hours to get. Yeah, so it's connecting in. I'm just looking at his connection. I'm looking at the it's very smooth. It's very it's really cool. That's very cool. So Blake, to end office hours, what kind of car should Brian buy? Brian's next car, 40-something-year-old Brian, the LaFerrari. I can't afford a LaFerrari. It already, if the name has Ferrari in it, I want something that like I've had a Honda Accord, I've had a Nissan Altima. I want something that is going to last, uh, be safe, probably V6. It could be V4. Sorry, I'm gonna drink my soy drink. Um, it could be V6, V4. It doesn't need to be V8. This LaFerrari looks awesome right here. Sedan or SUV? Sedan. My wife likes SUV. She likes the SUVs. I like the sedan, so I'm going sedan. Probably, like full sedan, not a coupe as they call it. So sedan, V4, V6. Like I've had Honda Accords, I've had Nissan Altimas. Um, Probably in the 15 to 50 range. Like it could be anywhere across there. It's a huge margin. We're not going for the 100,000, the 200,000, which more your SUVs. Man, used to be they'd advertise a new car back in the early 2000s below 50K. Yeah, that'd be below 50K would be good. I don't think I want to spend. This is my specialty. Nice. What would you suggest, Blake? What will be your car of choice with all your knowledge? Oh yeah, drop them in the chat. Just let me know. I don't know if I'll be buying a new car anytime soon because my Ultima's doing quite well, shockingly. Apparently, it had an issue with the transmission. Um, there was apparently because it's what is it? Nissan Altima transmission problem. Yeah, it's like this is right here. It's so 1010. Oh, cool. Yeah, maybe that sounds good right there. Kia Stinger. So this is Nissan Altima CV constant value transmission or something like that. We have something constant value CVT. Apparently there was a lot of problems, but mine hasn't done that. Honda will be more reliable. Yeah, I might go with the Honda Accord Sport. So that's the current. Is that the current Honda Accord Sport? See, and then here's the problem too. The issue I have is like you go to a dealership, and what if I just told them I'll pay you cash? BMW. Ooh, I haven't known about that. Let me look at this. The BMW M340i won't be super reliable. Why not super reliable? What would not be super reliable about the BMW? There we go. There's a 2020. Looks kind of nice. I bet the Honda Accord Sport's probably in Still Night Pearl. Ooh. Oh, that's nice, Blake. Yeah, that's good right there. See, look at that. It's got 79,000 miles, and someone's like 28,000. I'm just like, are you kidding me? Like, doesn't a new one cost like 30, 35? Or how much does a new? That's a 2019 for nearly 30,000, and I'm just like, so like, why can't around 35? So would you buy that 2019 right there, 28,000, or would you go buy a new one for 35? I know. That's the thing. That's what drives me crazy. Is you go to a dealership and you're like, sticker price is 35. And they're like, yeah, but we got only a few of these, so 42. And you're like, I'll buy. And they're like, okay, buy. We'll sell it to someone a month from now. And you're like, how much did you get it from the factory for? And they're like 31. You're like, okay, I'll give you 35. That's sticker price. They're like, nah, we don't want to sell for that. It's like, get some, what is it? Undercoating, all that stuff they do to it. I haven't seen used trims below 2 point that cost as much as more than the new ones. Yeah. Well, it looks really nice. So Honda Accord. What's it say? Really? Let me see here. Really stands out. Yeah, they're showing it right here. Let's see right here. I'm clicking on random YouTube videos, so I gotta watch out because is that it right there? think he's on a lot. He's looking at it. Is not a hybrid. I'm fine either which way. I do not know this dude's YouTube channel, so I'm going to be careful here so that I have no idea whose YouTube I'm watching right here. It's got a nice interior. He's just showing off the car. That looks nice right there. Turbocharged 4-cylinder, 252 horsepower, 273 4 pounds of torque, front torque. It looks good. This looks really good, Blake. Yeah, this is, you picked a good car for possibly what Brian might go with in the future. It looks very nice. Yeah, I'd go with a car like this. Feels, yeah, it does look, I like that look. Never know. I mean, I've thought about things like selling my car when we leave Texas and us just taking one car back to Knoxville and buying a car when I get back to Knoxville. Like if I could find a Knoxville dealership, don't search. Don't worry. I'll do all the, don't, because this is all Brian's personal. It's just talking like personal life, random stuff. Because it's like, okay, my wife and I will be driving back to Knoxville. And so, well, we've got 2 cars. We have 2 bunnies. So we want to make sure, the bunnies are doing all right. So one of the ideas is we sell one of the cars. This is just an idea. And then we travel back to Knoxville in one car. So that way, like the bunnies probably want a little bit of like, hey, bunny, you doing all right? Because, just want to monitor them. And also it's like a 14-hour drive. As long as you don't drive like a crazy person, you usually get at 30 miles per gallon. Yeah. So that's kind of what I'm like. That's kind of what I want. Like, it's the 40-year-old man car. The 40-year-old man car driving around in the, I'm, gonna get decent mileage in a car that looks nice right there. It looks like it's got some alloy wheels or whatever they're called. It's a cool car. Yeah, it's looking like the I'm a 40-year-old who still wants to be somewhat cool, but also not spend $1 billion on my car. That's a really good suggestion, Blake. I think you had, what was the other one? The BMW M340. Brian will always be cool. I appreciate that. Yeah, no, these are great suggestions. And the Kia Stinger, let me look down up and then we'll head off here. So the Kia Stinger, much more powerful. Power's good because, we might have to tow a boat or something like that. Of course, my wife has the SUV. Yeah, these are a little more expensive, but still, let's take a look right here. Yeah, that looks a little more cooler. Ooh, I just saw a leather interior. Ooh, that inside interior looks really nice. That looks 365 horsepower, 370. Is the torque like the torque being power, right? Because torque is like force. So it's like that's how much force it can exhibit. Oh, is it a 2-door? I think they make the sedan, right? Either which way. It does look pretty cool. I do agree. This one's cooler. But they are mad expensive for Kia. Yeah, so that's the concept car. Okay. It's the not on the street car. Yeah, these are pretty cool. It's the kind of car I'm going for. Just like a good value car that gets good mileage. Yeah, it does look pretty cool though. The red was real. Yeah, this one here. The yellow was a concept. Yeah, that one right there. Yeah, that's concept car. Kia Stinger. Yeah, awesome. The one is a twin turbo V6, so you can get lots of power, right? Twin turbo. I know V6 is like the 6 is the cylinders. I don't know what twin means. I don't know what turbo means. I mean, I know those words, but I do not understand them in like, if you're like, what's a V6? It's like 4-cylinder engine. What's a V8? 8-cylinder engine. Like, I don't know what twin means of it. Also, AWD and R. Oh, right, like all-wheel drive, right? Rear-wheel drive. I knew those. So it'd be good to have some all-wheel. Well, it doesn't snow that much in Knoxville. So in Knoxville, I mean, Honda is front-wheel drive. If you're pulling stuff, you want rear wheel drive, right? And preferably, if you're like in snow, like up north, we want all wheel drive because car goes off the back of the thing and you're like, and your wheels are just stuck. You're like, well, I'm done. Gotta get people to push you out. But you got that all wheel drive. It's gonna help you. You want rear wheel drive if you're drifting. You know me, Blake, too well. I've seen the cars right there like that. There's so well, I don't need rear wheel drive then, Blake. I'm not that cool. Don't drift, people. I mean, do it in a parking lot where you can be safe. Do all these things safely right there. But yeah. Do things safely. Brian's word of advice of the day. Kia Stinger has a drift. Oh my gosh. That's crazy right there. Well, that's really cool, Blake. I appreciate it. Well, Blake, thank you for the fun and thank you for the knowledge. If you want to drop what twin and turbo mean in with dealing with car engines, like I know what V6, V8 means, but what's it mean for it to be twin? What's it mean for it to be turbo? Like, if you got a V6 engine, what's a turbo? What's a turbo? Oh, so twin meaning two and turbo meaning turbos. But what's a turbo then? Like, you say your engine's a turbo. Like, I have a turbo V6. What's it mean to be turbocharged? I love asking I love getting knowledge and asking questions. I'll try my basically makes the car faster. Okay. So it's like your engines can rev up faster. So when someone's like they got turbo engines, like I got a V6 turbo, twin turbo. It's like double fast. So it's like, I guess a twin turbo can probably go from 0 to 60 faster than a turbo or just a V6, right? Like if you have a V6 and someone has a V6 twin turbo or twin turbo V6, they're going to go from 0 to 60 because the way the pistons work is it's the fuel injection, which causes the combustion, which gets the engine going. So isn't that, I know like a little bit of the physics of a car. Like I always want to understand like how the things work. And so it's like, the combustion within the cylinders causes the engine to get engine energy. It's Brian's technical terminology. Turbocharge is, I've heard supercharge before. Additional to the engine to the increased power. Turbocharge takes time to spool up and make their power as supercharger so supercharge is like the real deal. So if you're like on a track legal and you're racing someone, they got supercharge, they're gonna hit that gas and their car's just gonna boom. But when you're turbocharge is gonna like build and grow faster in its charge than just a regular engine. So your V6 supercharge, like twin supercharge, I don't even know if there is twin supercharge, but supercharge is like you're gonna hit and you're just gonna like feel like on a jet rocket. Where turbo is like you're gonna hit and start to feel it like powering up. Interesting. Turbocharge versus supercharge. Interesting. Yeah, I'll try to keep this in my head. Think about how it works. And I wonder how like the physics of it. More torque is faster off the line, and more HP helps. Horsepower. I think of HP like video games. Helps in the higher RPMs, rotations per minute, and speeds. Awesome. Well, I guess that's how the cylinders go, right? The cylinders are rotating, causing the energy. So yeah, because they go, and the cylinders rotate by the pistons firing. Man, in maybe in another life I would build cars because it is interesting, like the whole physics. Like to build cars and understand cars, you really have to have V10 right there. Yeah, 10 cylinders. So to build cars, I don't think people properly talk about how intelligent you have to be to do mechanics. Mechanics is all physics, and so I'm sure it's very mathematical. Like especially with like electric. My dad does electrical stuff. My dad does electric. He climbs up trees and chops them down. I've helped him take down some trees, but he's the one who's like 60s and 70s still climbing trees. Brian's the one being like, Dad, I'll pick up the wood. My dad, I'll chop stuff. I don't love using a chainsaw. I'm using the chainsaw like, my dad's like, you gotta go at it. Go put that little thing in the tree. And then you not chop down the tree from there. If you can spend extra money, go for the Lexus LFA. Best story I have is when my dad and I were putting a wall mount up for the TV. Ooh, that looks nice. My dad, look up the rev. Oh, I'm looking. It looks really cool. My dad and I were putting a wall mount for the TV up, Blake. So I was like, hey, Dad, let's wall mount my TV. And he's like, cool. He came down. And he's like, okay, you put the screws into the stud or whatever. And so I was like, my dad's like, look, son, here you go. And I was like, okay. He's like, okay. It's like, here, give it here. He's like, does them all. He should have had me do more when I was a kid. That's the only way you learn that stuff. The only way you learn that stuff is to like practice up and get good at it and like put screws into a wall a billion times, and then you have to do it and you're like, I gotta screw something into a stud, and you're like, But yeah, sound effects are immaculate. My dad is just really good at stuff. He's a statistician too, or more so than I am, because I'm business analytics. But he just all in with that because I value a lot of what he does. He knows woodwork. He does woodworking too. Like we actually helped out with that. Man, I was always afraid of the saw with the thing, and you're like feeding things through. Ooh, put on those gloves and watch your fingers. They got some now that like turn off immediately. Like if they touch something, they'll hold like a hot dog to it, and that thing will put like one little script on a hot dog and just turn right off. Like, or maybe not even. They've shown like, or watch, this is your finger, and they'll like move it towards it, and they'll be like, just powers off. It's just scary. Like, I don't know. Circular saw. There we go. Circular saw. We also had the other one, but circular saw just like feeding things through. You just have to be very careful because it'll catch like some wood. So I've fed a lot of things through. You know, keeping your hands. Watch out for that circular saw, and they bring the blade down. So I've worked with that. I don't know. I haven't worked with that in years. But I was like 8 or 9 working with the circular saw. Here, little 8 or 9-year-old, go work with the circular saw. We were fine. I didn't do it enough. So I always gravitated more towards computers. So yeah, that's safe. Yeah, but we usually, especially early on, we had a parent watching us. But then when we got to like be like 13, 14, because we'd make crafts for our family, we'd make like those triangle puzzles. So we'd get blocks of woods, you know, put the marks on them, and then do it out, and then sand them down, and remove the marks and stuff. So a lot of times we'd have like a production line of people like, you know, cutting the wood and then sanding the wood. You know, take some hard grit to start and some softer grain at the end. Softer grit, whatever they're called, sandpaper, like grade. I don't know. I know it's different grades of sandpaper. I don't know. I don't know, it's soothing to like make stuff and to have these skills. It's just as much as we learn about computers and technology, a lot of those bare necessity skills of being able to like cook, create, whether it be with metal or with fabric or, you know, wood, a lot of those skills are, I don't know, I value them. And I have creativity of my own. I create things with like videos and stuff. So everyone's got their outlets. So shout outs to everyone who creates in their own way. Yeah. So I don't know. I value the skill sets of a lot of people. I wish I had them. I covet them. So learn from each other. Thank you, Blake, for your knowledge. With that, we'll be back tomorrow. Bye for now, everyone. Bye, Blake. Great work. Create content. I created this visual effect. It's a reverse alpha key with a drone flyover video that someone had that I asked them if I could use their permission. They said, yes, you can. And I said, thank you very much. I'll create a reverse alpha with text over it. Reverse alpha in Adobe Premiere.